we learned the other day about two types of waves. This is one type of wave where you have essentially what looks like a water wave. It doesn't have to be a water wave, but a water wave is certainly an example of this kind of wave. The other one is where you have this series of high density areas followed by low density areas, then high density areas, then followed by low density areas, and so on. An example of this one would be a sound wave. Do you guys remember what this one's called? It's a transverse wave, right? A transverse wave, and the other one is called a longitudinal wave. Some people call it a longitudinal wave. Exactly the same thing. It's just a matter of how you pronounce it. Now, if a transverse, let's assume that both of these waves, the transverse wave and the longitudinal wave, are both moving to the right. Which way are the particles themselves vibrating within the transverse wave? Julia? Yeah, it's going to be perpendicular. It's going to be up and down like this. And it doesn't matter where you look, the particle at that particular spot in the wave is vibrating up and down. In other words, perpendicular to the motion of the wave. Versus the longitudinal wave, where the particles, no matter where you look, are vibrating which way? Parallel, yeah, parallel to the direction of motion of the wave. So they move, but only within their own little area, perpendicular to the wave motion or parallel to the wave motion in their own little area. When a wave carries energy from point A to point B, you don't get particle from point A going all the way over to point B. Okay, you get the energy going over there. The particle simply goes up and down, or left and right as the case may be, depending upon the type of wave, which transfers the energy to the next particle, which transfers the energy to the next particle, and then the next particle, and so on. So that ultimately the energy does make its way from A to B. Okay, let's take a look at this transverse wave again in a little bit more detail here. Okay, there it is. This is going to be my y-axis. This is going to be my x-axis. Can somebody please tell me if I start right here, where I'm going to stop to define a wavelength? A wavelength, remember, is the distance over which the wave repeats itself, or you could say it's just the length of a wave, right? Tell me where to stop. Tell me where to stop for a wavelength. Yeah, good. That's going to be one complete wavelength. That's the distance over which the wave repeats itself. What's that letter called? It's a Greek letter. Yep, Alex? Good, lambda, L-A-M-B-D-A, good, lambda. What's this called right here? The top part of the wave. The crest of the wave and the bottom part of the wave is called the trough, good. The amplitude of the wave is the size of the wave, and it's related to what? This is bigger, then the amplitude gets bigger. No? Yeah, it's the energy. The amplitude and the wavelength aren't related to each other, but the energy and the amplitude are. In fact, it's not even a linear relationship. As amplitude goes up, then energy goes up exponentially. But it's certainly related. They're certainly related to each other. Where would we label the amplitude here? The size of the wave, how big the wave is. Let's start right here. Okay, let's start right here. Tell me when to stop. Yeah, that's the amplitude of the wave. Don't go from trough all the way up to crest. Okay, that's wrong. That's twice the amplitude. You could go from crest down to the equilibrium, or you could go from trough up to the equilibrium. That's the amplitude. Got it? Now the other kind of wave, label a couple things on that one, and then we'll move on to the speed here. Remember, this was our, what was that called again? Yeah, that's our longitudinal wave. We've got these areas of high density and areas of low density. When my voice box makes the noise that you're hearing right now, what you have is air molecules in front of my voice box forming these high density areas and low density areas. And then the high density, it's not the particles from my throat that are going into your ear, but rather it's the high density area that's transferring energy to the next particles, to the next particles, to the next particles, to your eardrum. What is this called right here where we have a high density area? Good, it's compression. The wave is compressed there, right? You saw the other day with the slinky wave that the slinky was literally compressed. It's a compression. Now you can't really see it when we're talking about air and sound. Can't really see the air compressing, but in the end it is, just like the slinky wave was compressing. What do you call this area that trails it? right here that's low density. Yeah, be careful with that. A lot of people like to say refraction. Okay, that's a term that we talk about a little bit later on in physics 20. We talk about quite a bit in physics 30. Okay, it's not refraction, it's rare, not rare fraction, rare faction. Rarefaction. All right? Now, we didn't label a wavelength on this the other day, but I'm going to see if you can do this, okay? Let's say we start right here. Tell me where to stop for one complete wavelength there. Okay, I slowed down a little bit there. I heard one person whisper stop. That's where it would be, right? The distance over which the wave repeats itself. This would be the equivalent of going from crest to trough and back up to crest again, right? From compression to rarefaction and back to compression again. So the distance over which the wave repeats itself, a little bit harder to see on the longitudinal wave than it is the transverse wave, but same idea, right? All right, the last thing that we did on Tuesday before we performed our lab was to look at the speed of waves. And we said that the speed of waves is, once the wave is made, the speed, unless the wave goes from to another medium, the speed's going to remain constant. It's a constant speed, a constant velocity. Therefore, we can describe the motion of a wave by using the equation v equals d over t, unless it goes into a new medium. Right? We said when water waves go from deep water to shallow water, they change speed. Okay, it's not v equals d over t anymore. But as long as they stay in the same depth, as long as light stays in the same glass, doesn't leave the glass, as long as sound waves don't go from air to water, okay, then the speed is constant. So we describe it by v equals d over t. Very first equation we learned this year. But we can tailor this equation to this specific topic as well. D, we're going to say, is the distance over which the wave repeats itself. What is that distance over which the wave repeats itself? What's that called? It's lambda, right? And T is the time over which the wave repeats itself. What's that called? The period. So we're going to say V is equal to lambda over T. Now, we could use this, write this down exactly as it's written down now, but usually what we end up seeing, including on our data sheet, is a substitution in there for period. Say T is equal to 1 over F, which ultimately gives us this equation. V is equal to F times lambda. We had 3 equations, Bruce, for homework over the last couple nights, page 409, questions 1 to 3. Any issues with any of those 3 questions? 2 and 3 it is. Number 2 says a submarine sonar system sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock face and returns to the submarine in 8.5 seconds. Here's the wavelength. How far away is the rock face? It's clearly a speed of sound problem. And basically, we have 2 equations that we can use within speed of sound problems. V equals F lambda and V is equal to D over T. Let's write down some givens and see if we can figure out which one to try here. The frequency is 325. It looks like the time that it takes the sound to go there and back is 8.5 seconds. The wavelength of the sound, okay, this is not D, this is lambda, is 4.71 meters, and we're looking for distance. How far away is the rock face? Looking for distance, probably going to use V equals D over T, right? Rearrange this to solve for D. I get V times T. V is, I don't know what V is. Any ideas? Yeah, V equals F times lambda. Just like your group B equations way back in the second week of school, just like F is equal to KX and EP is equal to 1/2 KX squared. We've got a certain group of equations that we can use here. V equals D over T and V equals F times lambda are the 2 that we can use here. So understand what the concept is and then write down your givens and then figure out which one fits the givens. If it doesn't work, then try another one. We need V, so let's try the other one. You keep trying like this, like you really can't go wrong. F 325 times lambda is 4.71. What does that give me for the speed there? 1,530.75 meters per second. Thank you. It's pretty fast, eh? Speed of sound in air is about 340 meters per second, give or take. Okay, in water, we're saying it's about 1,530 meters per second. Wow, it's a lot faster. Of course, it varies, right? The temperature of the water varies. The density of the water varies. So the speed of sound would vary in there as well. But on average, about 1,530 meters per second, which is, what about 4 or 5 times the speed of sound in air? All right, so let's say D is equal to 1530.75 times the time now of 8.50 seconds. And when I do that, I should get about 13,000 meters or 13 kilometers. Something like that. Yeah, but that's not the answer. The answer is 6.51 kilometers. What did I do wrong? Yeah, it's my time here. The time that I have is the time that it takes the sound to go to the rock face and back. Okay, what am I looking for? The distance to the rock face, not the distance there and back. So I'm okay here. I can divide this distance by 2. This is my return distance. Divide it by 2 to get my one-way distance. Or alternatively, if you catch that right away, then you can just divide the time by 2 and get 4.25 seconds. Just don't do both, right? Because then you're going to end up with half the distance you're supposed to end up with. Okay. How many people got the 6.51? How many people got that? I think we talked a little bit about the dividing by 2 thing on Tuesday anyways, right? 3. Here's a good one. A fisherman anchors his dinghy in a lake 250 meters from shore. The dinghy rises and falls 8 times per minute. He finds that it takes a wave 3 minutes to reach the shore. How far apart of the wave crest? Wave speed problem, right? So we know we're going to use those 2 equations, or at least we're allowed to use those 2 equations, d over t and v is equal to f times lambda. What do we have given to us here? Looks like the wave travels 250 meters. That's not a wavelength. It's how far the wave travels. The time that it takes the wave to travel that distance is 3 minutes or 180 seconds, because we don't want to be in minutes, right? It's this 8 times per minute thing. The dinghy rises and falls 8 times in 1 minute, or 8 times in 60 seconds. What does it do? It's the frequency. We're going to say frequency is 8 divided by 60. Right? 8 divided by 60 because it's 8 times in 1 minute. And what does that give me here? I think it's 0.133. And we're looking for how far apart of the wave crest. What is that? It's the wavelength, yeah. How far apart of the wave crest? The distance over which the wave repeats itself. We're looking for lambda here. So I'm going to say v is equal to f times lambda. Lambda is equal to v over f. I've got the frequency, don't know the speed. I'm going to find the speed by using d over t. So it's kind of the opposite of the last question. 250 meters divided by 180 seconds gives me 1.3888. Thank you. That's in meters per second. So we're going to take that number now and divide it by the frequency of 0.1333, and we get 10 meters. Almost exactly 10 meters, but rounded to 2 digits. It is 10 meters. Good? How many people got that one? Oh, you guys are set then. No problems.